So a non-deterministic programming is something that that you don't usually um, see when you write normal programs, normal computer programs, and that's mainly because uh, normal computers, normal programs are ran by CPU, which is a deterministic object. By deterministic, I mean that every state is only a function of the previous states, which makes sense. Um, but in Cairo, the situation is slightly different because we are not using Cairo in order to run a certain program. We are using Cairo in order to prove to another party that the run was successful. Um, so I'm going to first describe what's a non-deterministic programming is, and then how it can help you write programs in Cairo. It's not something that you must use, but it can make your programs much more efficient. Um, so it starts from a very famous question, an open question in complexity theory, which asks whether or not two classes of problems are the same. They are called, the two classes are called P and NP. And these are classes of problems. So in order to, before I define them, I'm going to take a certain problem as an example. So the problem is going to be the Hamiltonian cycle problem, and it goes like this. You are given a graph, which is a set of nodes and edges that connect the nodes, and you are asked whether or not there exists a path in the graph, a cycle, which visits every node exactly once. So here is an example of a graph, and in this case, there is a cycle, there is an Hamiltonian cycle. So the answer is yes. And if if you want to solve it, the naive approach is just to search over all possible cycles in the graph and check if any of them satisfies the condition. But this takes too much time. It's an exponential solution, which means that even for relatively small instances, it's going to be infeasible to run this algorithm. And this brings us to the definition of the first class, which is P, that all the problems that can be solved in polynomial time. So is this problem in P? So the algorithm that I've just described does not show that that it's in P because it's an exponential and rather than polynomial algorithm. But it doesn't mean that there are no other algorithms that solve it in polynomial time. And the answer is that we don't know. It's an open question whether or not this is solvable in polynomial time. But now let's talk about the second class, which is NP. And I'm going to give two equivalent definitions for this class. The first definition is it's a problem is in NP if someone untrusted someone can convince you that the answer is yes in polynomial time, assuming that the answer is indeed yes. So if you're given this graph and I'm trying to convince you that there is a cycle, then I can simply show you the cycle, and you don't have to trust me. You just have to check that this is indeed a cycle that visits every node exactly once. And this is a very easy task. This is a linear time task. So I can convince you that the answer is yes in polynomial time, which means that the problem this problem is in NP. Now I want to give another definition. And in this definition, there are no two parties that one is trying to convince you that the answer is yes. You have to decide for yourself, but you are given to do this. You are given a magic coin, and you can use the magic coin. You can toss the coin in order to say whether or not there is a cycle in the graph. Let's say that you have to find a cycle or fail if it doesn't exist. Um, and the question is, how does what does this magic coin do? So this magic coin knows it's magical. Knows in advance your algorithm, and it sees what you're going to do and what you're going to decide, and it tries to do whatever possible to make your program not fail, to make sure that the program succeeds. Um, so let's say that you are given such a coin and you want to solve this Hamiltonian cycle problem. Then you just do as follows. You start with some node in the graph. Now you toss the coin to choose an edge that goes out of this node, and go to the node at the end of this edge. And then you repeat this until one of two things happen. One option is that you found an Hamiltonian cycle, so the coin just guided you through a valid cycle, and then you just return, hey, success, I found the cycle. The other option is that for some reason you go back to a node that you visited before finishing the full cycle. So, for example, you start from the first node, go to a second, and then go back to the first, even though there are more nodes in the graph. In this case, you simply fail. Now, let's examine what's happening. So, if you answered yes, it's after you found an Hamiltonian cycle. So, in this case, we are convinced that the answer is indeed yes. If your program failed, it means that the coin was unable to guide you through an Hamiltonian cycle in the graph, which means that there was no Hamiltonian cycle in the graph. So indeed, in this case, the answer is also correct. You should have failed. And by the way, if we can say that if the coin is unable to find to do something to make the program succeed, then let's say that it picks something at random. It doesn't really matter because the program in this case is going to fail. Okay, so as I mentioned before, when you're writing when you're writing in Cairo, you should think as if you were in the second situation of NP and not the usual situation of P. So you should think as if you are given this magic coin, and you can use it to make some decisions during during your program, which is cool. So in this case of Hamiltonian cycle, we can move using a coin. We can move from an exponential algorithm to a basically linear algorithm. You just need to flip the coin according to the number of edges or nodes. Depends on how you count it. Okay. My guess is that you are not going to see a lot of Hamiltonian cycles problems when you write code, when you write Cairo code. So let's take a look at something more practical, which I guess that you will encounter. So let's say that we have an array of pairs x and y, as you see in the slide, and the question is, assume that x equals 5 at some point. So indeed, you see that here x is 5, just return the corresponding y, which is 1. So if you want a simple, a normal program, a normal algorithm for this, just scan the array and stop when x is 5 and return the corresponding y. This takes linear time, which means that unlike the previous example where we saved, so we moved from exponential to linear, in this case we are already linear in P without non-deterministic programming. But still, you can use non-deterministic programming to get even better than linear algorithm for this. So what you're going to do is toss the coin to let it choose an index to the array. Then if the index does not fall in the bounds of the array, you just fail. If the index is not on 5, on x equals 5, you also fail, and then you return y. Now, since we know that the coin is going to try to make sure that your program doesn't fail, we know that it's going to pick the right index. Otherwise, your program will fail. So unless 5, so if 5 is not in the array, then it will fail. But if 5 is, then we know that this algorithm using these coin flips will indeed return the correct y. Now, note that we moved from a linear time algorithm to an algorithm with O of 1 instructions, which is great. By the way, this is there is a library function in Cairo that does exactly that in constant time. Cool. I want to show you now that non-deterministic programming is, let's say, less intuitive than normal programming. And for this, I'll slightly change the problem. Instead of returning the corresponding y if x is 5 and failing if there is no entry in which x is 5, I want the algorithm to return 0 if there is no such entry. So let's try to change the code, the pseudocode. So instead of the last two lines, I wrote, if x is not 5, then you return 0, otherwise you return y, which is what you would have done if it was normal deterministic programming. But now what's going to happen? Since all the magic coin cares about is making sure that we don't fail. It doesn't care about making sure that we'll return the right result. It only makes sure that we don't fail. And now, in this case, for example, the coin can choose the first index, and then the program will not fail. It will just return 0. So if x is it's in the bounds, so it's okay. X is not it's not 5, it's 4. So return 0. It's not a failure. So in this case, it's possible that the coin will lead us to return 16, which is the wrong result here. So we have to be careful about the way we are using this magic coin. This magic coin is very powerful and can save us a lot of computation, but we need to use it correctly. By the way, it is possible to solve this slightly modified problem in a mixture of the normal approach and the non-deterministic approach. You first flip the coin to let it say if 5 is in the array or not. If it's in the array, then you continue with the usual algorithm. And if it's not, you just scan the entire array and then you have the linear time algorithm, and then the algorithm will be correct, although in some cases it will be linear, and in some cases it will be constant time. Okay, cool. So the next thing I want to talk about is how do we use non-deterministic programming in Cairo. So basically, the magic coin is just using uninitialized memory cells. If you take a memory cell in Cairo and and you didn't initialize it with some value before, you can think about the value of the cell as the value of the magic coin. So for example, if I wanted to implement the algorithm with the searching in the previous slide, all I have to do is pick one cell, uninitialized cell, and then treat it as the index, make the bound check on it, make sure that it points to an entry with x equals 5, and then return y, and otherwise, of course, fail. Now, the second thing is that, well, there are no, actually magic coins do not exist. And the reason Cairo is able to take advantage of non-deterministic programming is only the fact that there are now two parties. There is the prover, which tries to convince the verifier that some claim is true. Now, from the verifier point of view, magic coin can exist from its point of view, but the prover is going to use normal hardware, real hardware. So the prover does not have access to this magic coin, which means that you have to tell the prover how to simulate this coin. And the way we are doing this is using what we call hints or prover hints. Hints are pieces of code. In the case of Cairo, we are using Python code that you can put inside your Cairo program. It's not part of the Cairo program. It's just something that helps the prover simulate this magic coin. So for example, if I go back to the example with the array, the magic coin had to pick the index. Now, Cairo won't know how to find the index itself. You will have to guide it, and you will have to write code that finds the index and put it in this otherwise uninitialized memory cell. By the way, it means that from the prover point of view, the algorithm is going to be linear and not constant time. It's really not possible to solve this algorithm in constant time, this problem in constant time. But from the verifier point of view, it is going to take only a constant amount of Cairo instructions to find the element that corresponds to 5. And this brings me to the last slide, which talk about correctness of programs. When you write normal computer programs, deterministic programs, there is basically only one notion of correctness. You either run the code and get the correct result or not. When you are using non-deterministic programming, such as in Cairo, there are two properties that you should make sure that your program satisfies. One is called completeness. Completeness is the simpler question of whether the code with its hints executes successfully. So for example, if I take this search problem, if I change the hint and instead of putting the correct index, I just always put 0, for example, then I will not have completeness. Um, and the second thing is called soundness, and it says that even if the hints are replaced, um, the code will still always, if it does not fail, so it's possible that the code will fail if the hints are replaced, but if it does not fail, then it will return the correct result. Let's go back again to the example with the to the search example, and for example, let's say that I remove this line. I'm going to the good example, the first one. So let's say that I remove this fail if x is not 5. So from the point of view of completeness, if I run if I run this program, it will always succeed because um, the hint will always point to the correct location. So it will never fail on this, and it will always return the correct result. So for example, if I wrote unit tests, all my unit tests will pass. But this is but now I don't have soundness. Why? Because if I change the hint and I don't have this line, it's possible that the coin, for example, was maliciously set to 0, to toss 0, and then I'll get, for example, in this case, 16 instead of 1. When your program is not complete, it means that you may not be able to generate a proof. But when your program is not sound, it means so you will be able to generate a proof for the run, but the proof will mean nothing. And basically, you need, when you write programs that take advantage of non-deterministic programming, it's important to have both completeness and soundness.